The universe is a vast and mysterious place filled with wonders that boggle the mind. Amidst this cosmic tapestry there exists a fundamental concept, a mathematical entity that underpins the very fabric of reality, the vector. Vectors are more than just arrows on a page. They are the language of motion, force and displacement, describing how things move and interact in the grand theater of the cosmos. Imagine a lone spaceship traversing the interstellar void. To chart its course, we need to know not only how fast it's traveling but also its direction. This is where vectors come into play. A vector, represented by an arrow, encapsulates both the magnitude, size, and direction of a quantity, providing a complete picture of motion. Vectors are the unsung heroes of science and engineering. They are the tools that allow us to model the flight of a rocket, the flow of air over an airplane wing, and the intricate dance of particles within an atom. Without vectors, our understanding of the universe would be incomplete, like a map without compass directions. To truly grasp the power of vectors, we must first understand their two defining characteristics: magnitude and direction. Magnitude, represented by the length of the vector arrow, tells us how much of something we have. For example, the speed of our spaceship is its magnitude of velocity. Direction, indicated by the way the arrow points, tells us which way the quantity is acting. A spaceship traveling at the same speed but in a different direction will follow a completely different path. This underscores the importance of direction in defining a vector. Think of a vector as an instruction, a command to move a certain distance in a specific direction. This concept is fundamental to understanding how vectors work and how they help us describe the world around us. Let's embark on a journey into the fascinating world of vectors, where arrows come alive and mathematics takes on a new dimension. Imagine a treasure map, not with cryptic symbols but with vectors guiding us to buried riches. Each vector on the map represents a displacement, a change in position. To find the treasure, we must follow the vectors one by one, adding their displacements together. This process, known as vector addition, is like taking a series of steps in different directions. The final position we reach relative to our starting point is the vector sum, or resultant vector. Vectors are not confined to the realm of abstract mathematics, they permeate our everyday lives. Consider the simple act of throwing a ball. The velocity of the ball, a vector quantity, determines how far it travels and in what direction. The force we apply to the ball, another vector quantity, influences its speed and trajectory. Even the wind resistance the ball encounters can be represented by a vector, acting in the opposite direction to the ball's motion. Adding vectors is a fundamental operation that allows us to combine vectors and understand their combined effect. Imagine, if you will, two teams playing tug-of-war. Each team's pulling force can be represented by a vector, with the length of the vector indicating the strength of the pull. The resultant vector, found by adding the two force vectors, reveals the net force acting on the rope. If the resultant vector points towards one team, that team is winning the tug-of-war. Subtracting vectors, finding the difference. Vector subtraction, while seemingly more complex, follows a similar logic. Imagine two cars traveling on a highway. Their velocities can be represented by vectors, indicating their speed and direction. To find the relative velocity of one car with respect to the other, we subtract their velocity vectors. This subtraction allows us to determine how quickly the cars are approaching or moving away from each other. Vector subtraction is crucial in fields like navigation and air traffic control, where understanding relative motion is paramount. The dot product, a cosmic dance. As we delve deeper into the world of vectors, we encounter more sophisticated operations that reveal hidden relationships between them. The dot product, one such operation, provides a measure of how much two vectors agree with each other in terms of direction. Imagine two flashlights shining on a wall. The dot product of their light beams is greatest when they point in the same direction, producing a bright spot. As the angle between them increases, the dot product decreases, reflecting a diminishing overlap of their light. The cross product, a new dimension. The cross product, another vector operation, takes us into the realm of three dimensions. Unlike the dot product, which yields a scalar, the cross product results in a new vector, perpendicular to the plane formed by the original two. Imagine using a wrench to tighten a bolt. The force you apply and the length of the wrench handle can be represented by vectors. The cross product of these vectors gives us the torque, a measure of the twisting force applied to the bolt. Vectors, the unseen architects of our world. Vectors, though often hidden from view, are the unseen architects of our world. They govern the motion of planets and stars, dictate the flow of fluids, and underpin the behavior of electromagnetic fields. In the realm of technology, vectors are essential for designing everything from skyscrapers to smartphones. Understanding vectors empowers us to comprehend the intricate workings of the universe and to harness its power for the betterment of humanity. As we continue to explore the cosmos and push the boundaries of knowledge, vectors will remain our steadfast companions, guiding us through the boundless expanse of scientific discovery.